Okay. All right, chapter 9, disproof. So the idea here, no, this is a good one. This is a really fun one. How would you prove a statement wrong? Okay, that's what we're working on. How would you prove a statement wrong? Yeah, so for this first one, how would you prove that the statement, every single X in my set has property P, how would you prove that wrong? Yeah, you need to find 1X where P of X is false. Well, no, so we're going to handle the different types. Okay, so this statement here, notice if I negate it, let's think back to our logic. If I negate it, I get there exists an X in S such that not P of X, right? So what you just told me, common sense how to prove it wrong, that is the negation, okay? That there's some X with not P of X being true or P of X being false, okay? So here I have a statement that I want to prove false. For every X and Y in the real numbers, the absolute value of X plus Y equals absolute value of X plus absolute value of Y. So here's where you just play around with it till you find something that works. So, or doesn't work, however you want to view it. What would be something that shows this statement is actually not a true statement? Yeah, so there you go. Yeah, heard X negative, Y positive, and I heard -1 and 1. So same thing, right? Anything like that. And that's absolutely right. You need to have one being negative, one being positive, but any combination of negative, positive work. So I heard -1 and 1. So let's take that. So we normally wouldn't write proof with this typically, because you know, it's kind of a proving it false, right? We're not proving, we're disproving. So we can just say, note that X equal -1 and Y equal 1 gives, here we go, absolute value of X plus Y equals 0 and absolute value of X plus absolute value of Y equals 2. Yeah. Yeah. So the point of this chapter and the point of disproof, right, is building up to this actual, well, here's our word, counterexample. That's example showing a statement is false. So typically, you're not asked to disprove something. Typically, you're asked prove or give a counterexample. So the counterexample does not need to be written remotely like a proof. You would just say, hey, X equals -1, Y equals 1, and then show, yep, shows it's false. You know, it's not a proof or anything. It's just a counterexample. Okay. Well, so I have before, you know, asked questions on tests where it says prove or give counterexample. And some of them are counterexamples and not proofs, you know, so yeah, because it saves you time. So, all right. Well, yeah, if you see the counterexample quickly, it saves you time. Good point. All right. So how would you prove a statement P of X implies Q of X wrong? Okay, yeah, so you're focusing on the true implies false situation. Yeah. So you would need to find, so find X with P of X true and Q of X false. And all it takes is one X, right? Because if I say P of X implies Q of X, I'm claiming that if I get any X giving me P of X being true, then I'm claiming Q of X will also be true. That's what that implication means, right? Because if P of X is false, then it's always true. Who cares? But if P of X is true, I have to get Q of X true. So all it takes is one X where that doesn't work. So here I have a statement. Let n be an integer. If n to the fifth minus n is even, then n is even. What do you think? It is false. 3. Yep, 3 works. In fact, any odd number is going to work because odd minus odd will still give me even. Okay. So yeah. So we could just say counterexample. CE if you want. Yep. Counterexample n equals 3. 3 to the fifth minus 3. Well, 3 to the fourth is 81. 243. 243 minus 3 equals 240. Yep. So there we go. N to the fifth minus n is even. N is definitely not even. All right. This is a good chapter. We like chapter 9. All right. Any questions on example 2? Okay, so start thinking about example 3. Give you a second to think. True or false? All right. So example 3 is false. Okay. It should look a little funny to you because when we did sets, we actually had a union there, if you remember De Morgan's laws. So should look funny. So let's try to come up with a counterexample. All right. So let's let my universe, I don't want to be too crazy. Let's just let it be 1, 2, 3, 4, 5. And then you start playing with things for A and B. What's going to end up happening, I think, as long as they overlap, we'll be able to get a counterexample. So let's make A 1, 2, 3. And let's make B 3, 4, 5. Let's see if that works. So what? A intersect B complement. Well, A intersect B is 3, right? So the complements 1, 2, 4, and 5. All right. What's A complement? 4 and 5. What's B complement? 1 and 2. What's the intersection of that? Empty. Definitely not the same thing. So we did find a counterexample. Okay. Now, here's what happens then if you have a statement, oftentimes it says true or false. So you jump in, you say, I think it's false. And you start playing. If you can't find a counterexample, you keep messing with it, messing with it, messing with it. And you can't find, you go, well, maybe it's true. So then you go to trying to prove it. And then you get stuck in the middle of your proof and you go, maybe it actually was false. And you take that thing where you got stuck and say, maybe that's the issue and try to build your counterexample around that, right? And so, people doing math research, when they spend months and months and years working on a problem, that's what they're doing. They're going back and forth, counterexample proof, back and forth. And using that to help give more logic into the other. You know, when you try to build your counterexample, you start to see patterns and go, well, maybe those patterns will work. And then you go to your proof and you work on those patterns and get stuck and go, oh, maybe that's a problem. And so, yeah, so it is a back and forth play as the proofs get more complicated. For our purposes, for this class, obviously you shouldn't have too much back and forth. Okay, but a little is natural at this level even. All right, the last type. So how would you prove a statement? There exists X in a set such that P of X. How would you prove that statement wrong? You need to show it every single X, P of X is false, right? Yeah. So for all X, P of X is false. Or in other words, the negation of that, which is for every X, not P of X, okay? So this means I can't just come up with one example, right? I have to show that nothing will satisfy it. So here's a statement that is actually false, okay? So says there exists a real number such that that inequality is true. If it had said x to the fourth smaller than x squared smaller than x, it would actually be true, like a half would work for that. If it had said x less than x squared less than x to the fourth, it would be true, you know, 2, 3, anything like that would work there. But putting that x in the middle does make this false, okay? But in this case, we would need to do a proof. A counterexample isn't enough because we have to prove it for all x. So we would say proof, and it's kind of like a disproof. So we need to take a random x in the real numbers. Okay. And this is often how you start this type of proof. We're going to assume for contradiction x to the fourth is less than x squared. And we're going to show this is impossible. Okay. Well, if x is bigger than x to the fourth, it's definitely positive, right? So we'll say note x is bigger than x to the fourth, so x is bigger than 0. All right. Dividing by x yields x cubed less than 1 less than x. Which means, so now I'm going to subtract 1 from everything. X cubed minus 1 is less than 0 is less than x minus 1. All right. Notice x minus 1 is bigger than 0. That's what this says, right? X minus 1 is bigger than 0. So I can divide by it without messing up my inequality. So since x minus 1 is bigger than 0, we can divide by x minus 1 to get, here we go, x squared plus x plus 1 less than 0 less than 1. All right. It's okay if you didn't remember how to factor x cubed minus 1, but it does factor to x minus 1 times x squared plus x plus 1. Okay, so that is how it divides. Now we are one step from being done, because look, we said x has to be positive. What's that mean about x squared plus x plus 1? If x is positive, That's definitely positive, but I have here that it's negative. So there we go. There's our contradiction. But x greater than 0 means x squared plus x plus 1 is greater than 0. So there we go. But our contradiction symbol, we've reached the contradiction, two statements that don't agree. All right. So thus, no x can have the property x to the fourth less than x squared. All right. Any questions on that? So if the statement had been true, an example would have proven the statement true because it was a there exists statement. But in order to prove it false, I had to prove there do not exist any x's that make it true. So you do, when you're doing the disproof stuff, you need to look at your statement carefully. Is one x enough to disprove it, or do you need to show all x's to disprove it? So, yep, but that's disproof. It's not bad.